This lesson is going to cover a specific type of function called a linear function. A linear function is a function of the form y equals wx plus b, where w is the slope and b is the y-intercept. If you don't know what some of these words mean, like you don't know what slope means or y-intercept, that's totally fine. I'm going to add another video after this one that's totally optional to cover some of these more basic concepts. But one of the biggest goals of my channel is to make sure that anyone with even just a basic algebra background can follow along with these videos. So I'll add that on probably later this week. So let's look at a graph now of a function, of a linear function. So here is the y-axis, here's the x-axis. And let's say we want the linear function, we want to graph this linear function, y equals x plus 1. So let's go ahead and label the x-axis. And let's graph this. So y equals x plus 1. So this is a function that is a linear function because it's of the form y equals wx plus b. So in this case, w is 1 here, so we don't even bother to write it because anything multiplied by 1 is itself. And b is also 1 right here. So just to quickly walk through this, when x equals 1, it looks like, 1 plus 1 is 2, so y equals 2. Draw a point here. Draw a point here. When x equals 2, y is 3. And then let's do a few in the other direction too. When x equals 0, y equals 1. And when y equals negative 1, when x equals negative 1, y is equal to 0. So we kind of have like a rough idea what this is going to look like. So let me draw a line that goes through these points. And this is what a graph of a linear function is going to look like. Now the key intuition here, let me write this out, key intuition. Changing w and or b is going to change the shape and position of the linear function. Let me show you a visual example of this. So here I have the line y equals x plus 1 graphed, and you could see, let's say I increase b. Let's say instead of x plus 1, it's x plus 10. So you could see the line jumped up here where, like before it was down here near the origin, but now the line intersects with the y-axis at 10 at x equals 0. And similarly, let's say instead of w equaling 1, let's say we set w to maybe 5. You can see the line got much steeper. So the key thing to keep in mind here in regards to neural networks is that in a linear function, when you change w and b, you're going to change the shape and position of the function. So in this example, let's say we are trying to model the price of a house based on its square footage. With a linear function. So just to kind of write this out, the linear function is going to look something like this, of course, y equals wx plus b. And the input here is going to be, the input into x is going to be the house's square footage. And the output here is going to be the price of the home. So we have a graph of this here. So on the x-axis, we have square footage, and on the y-axis, we have the price of the house. And we have 3 data points. So we have house 1, which is about 1,500 square feet and costs about 150,000. House 2, which is about 2,500 square feet and costs 300,000. And house 3, which is about 3,000 square feet and costs about 500,000. And what we want to do is, given this data, we want to create a linear model using a linear function that is going to model house prices. And what that basically means is we want this linear function to go through these 3 points as best as we can. And the reason that that's valuable is given that this is high quality data, if we want to predict what, like, say, house 4 is at around maybe like 4,000, 5,000 square feet, we could say that, well, because the linear function went through these other 3 points so well, it's giving us a pretty good prediction of what house 4 could be. So let's go ahead and try that. So on this left side here, we want to get this linear function to best go through these 3 points. How can we do that? Just like we talked about, modifying w and b. So let's start with modifying b. So instead of 10 here, let's make it maybe 70,000. And then for w, instead of 5, let's try 100 or 110. And we can see when we modify w and b, this linear function now kind of does a pretty decent job of going through all 3 of these points. Okay, great. So now you've seen what the definition of a linear function is, and you've also seen a concrete example of how you can change w and b in a linear function to fit data, like how we just saw with house prices. So how does that relate to neural networks? Well, if you recall, a neural network looks something like this, where each of these circles represents a neuron, and each neuron has an input and it outputs a value also. So this neuron, for example, could take in some value like square footage of a house, and it internally does some processing on it, and then it spits out an output to this next neuron, which does some internal processing, which does the same thing to this last neuron. And then this could spit out, for example, like the price of the house, if that's what we want our neural network to predict. So this internal processing that happens in a neuron is a little complex, and we'll get to it later. But part of what's going on in there is a linear function. So the linear function in this example could be of the form y equals wx plus b. And actually, every single one of these neurons has a linear function inside of it, a different linear function. So let's actually make this a little bit more concrete and give each of these neurons its own linear function. So say the one inside this is currently y equals, let's just say y equals w1 x1 plus B1. And then we'll say this is y equals W2 x2 plus B2. And we'll say the one in this third neuron is y equals W3 x3 plus B3. So all three of them have a linear function inside of them. And again, I want to say real neural networks also, almost all of them have a linear function inside each neuron. And then that linear function is usually there's another function on top of that linear function called an activation function, but you don't have to worry about that at all for now. For this simplified example, just pretend uh, each of these neurons just has this simple linear function inside of it. And again, I want to say that they're all different linear functions. Like W1 and B1 are just for this neuron specifically, and W2 and B2 are just for this neuron specifically, and W3, B3 are just for this neuron specifically. Every neuron's going to have its own linear function inside of it that's unique to that neuron. So if we really look at what's happening here, you're kind of constructing this massive equation. So what we're going to do is we're kind of throwing this inside of, we're outputting this to this function. So it starts looking something like this. W2 times W1 x1 plus B1 plus B2. And we're putting we're putting this whole more complex equation, we're outputting that to here, to this final neuron. So the total equation starts looking something kind of like this. W3, we throw that into that last neuron's linear function plus B3. And this is what the neural network is going to spit out. This y value is what is going to come out here on the other end from this neural network. So let me write this out. Each neuron can contain a linear function inside of it. And I do want to give two notes here. So one is that in actual neurons and real neural networks, like I kind of said, it's not just a linear function that's happening in each of these neurons, but we'll get to that. And the second thing I want to note is technically it doesn't have to be a linear function inside each neuron, but in almost all modern neural networks it is. And we'll get to why that is in later videos too. But for this simplified example, what's important to know is that each of these neurons has a linear equation inside of it, a linear function inside of it of these forms, and the totality of this neural network leads to this gigantic linear equation with this output. That's what you have to have followed so far. So the next thing is, just like we saw how you can adjust a linear function, the w and b variables of a linear function, to fit data. So like those three house prices we saw, we adjusted w and b to make that line fit them as best as we could. What happens when you train a neural network is you give it data. So for example, we could give this neural network those three house prices, and for every single one of those neurons, we're going to do exactly what we did with just our simple linear function. For every single one of these neurons, we're going to adjust W, all these W values and all these B values to fit that data that we gave the neural network. So let me write that out also. Each linear function contains variables W and B, and training a neural network is the process of adjusting W and B for each neuron to best fit the data given to the neural network. And the last thing, which again I'd really briefly mentioned in an earlier video, is this training process of adjusting W and B for each neuron is done through calculus. So I know that was a lot, but don't worry, we're going to go into each of these concepts in a lot more depth. And the main takeaway, though, from this video, if you take one thing, is that neurons in neural networks contain linear functions, and linear functions, the shape of linear functions change through modifying W and B.